Okay, as I was saying, we have a lot of topics in the lesson today, so we do have kind of lengthy notes. We're going to be talking about exponents, exponent properties, how to combine them. We're going to talk about when we have square roots, cubed roots, fourth roots, how do we write those with exponents. We're going to talk about complex numbers, which are a special kind of square root that they come from. And then we're going to totally switch gears, and we're going to talk about two geometry topics. If we have two similar figures, we know scale factors for those. How do the areas relate to each other? And then we are going to take a rectangular prism, such as this box, and we're going to look at how long is a diagonal, not in one of the rectangular faces, but if we went from the top left front corner to the bottom right back corner so that it goes through the space in the middle of the box. How long is that diagonal? So let's start in with our exponents. And just as a quick review, if we have x to the minus n, that's 1 over x to the n. Or if we have the negative exponent in the denominator, that can go up to the numerator and be positive. It works whether we are saying we have x cubed is 1 over x to the minus 3, or 1 over x to the minus 3 is x cubed. If we have something with an exponent, we can move it from numerator to denominator as long as we change whether the exponent is positive or negative. For the next one, before we worry about both the n and the m, what would we do if we just had the square root of x, and we wanted to write that with an exponent instead of a square root sign? Does anyone remember how we would do that? Mia? It would indeed be x to the 1/2. What if it were the cubed root of x? How would we write that one with an exponent? Ashani? It would be x to the 1/3. So the root becomes the denominator of the exponent. So if we have both, x to the m is still x to the m. The root would become the denominator of that. Next, for our basic imaginary numbers, does anyone remember how we defined I? Caleb? So our definition of I is the square root of -1. So if we want powers of those, if we want I squared, that is going to be I times I. So it is root -1 times root -1. Remember, root 2 is regular 2. Root 5 is regular 5. So root -1 is a regular -1. If we want I cubed, that is I times I squared. So that will be I times -1. So that will give us that I cubed is minus I. Then if we want I to the 4th, that is I times I cubed. So I times minus I is minus I squared. So it is the opposite of I squared, so it's the opposite of -1. So we are back to +1. And then we repeat. I to the 5th will be I times I to the 4th, so we'll be back to I. I to the 6th will be I times that. So what happens is, every time that our exponent is a multiple of 4, I to the 8th, I to the 12th, I to the 16th, and so on, it is 1. So if we are simplifying I to great big powers, we factor out I to some multiple of 4 and see what we're left with. So far, so good? Okay, we will do the ratio of areas formula and the diagonal formula in a little bit, so just set those formula pages aside, and we will come back to those. Let's work with these properties first, with simplifying some things. One thing that I want to caution you about in your book it is sometimes hard to see, oh, is that y cubed or is that the cubed root of y? And the book is worse than the smartboard type for being able to tell that. So if you aren't sure, take the edge of your paper or anything that's a straight edge and just bring it over. One place you can line it up with is the very right edge of your radical sign. Oh, that 3's not in there under that square root, so it is not part of that square root. Or you could line it up with the very edge of your radical. Oh, it's still part of that. It's not over here before you get to the radical. So it does have to be part of that. So just to kind of help you try to see that. What that means is for this problem, this is one piece, and this is the cubed root on that. So when we have ones like this, first step is to write the square root, cubed root as fractions for our exponents. So we have x to the 5th y to the 1/2, and we have x squared y to the 6th to the 1/3. Question or just stretching? Okay, just checking. Don't want to lose you here. So then we apply the exponent to each thing that's in here. So we have x to the 5th to the 1/2, so we multiply those and have 5/2. And we have y to the 1/2. And then here we apply the 1/3 to each part in there. And we have x to the 2/3, y to the 6/3, but 6/3 simplifies as 2. Is it okay to have more than one x and more than one y in there? Not for a final answer. It's okay temporarily, but we can't stop there. So we have to combine the x's and combine the y's. So when I have x to a power times x to another power, what do I need to do with those exponents? I need to add those exponents. So I am looking at x to the 5/2 plus 2/3, and I am looking at y to the 1/2 plus 2. When we're adding fractions, what do we have to worry about, everyone? Common denominator, exactly right. So I need to multiply by 3/3, by 2/2, and I have 15/6 plus 4/6, so 19/6. And 2.5 I know is 5/2, a half plus 4/2. Now I only have x once and y once, so that is my answer on that one. Questions there? Okay, let's get progressively harder with these examples. Instead of just numbers in our exponents, let's have some variables in the exponents. So we're going to basically do the same thing. We're going to figure out how do we start putting things together. So in my numerator, I have a to the x over 2. That's fine. This is just one exponent on the y inside that parentheses. So I have y to the m to the n. So I need to multiply these exponents. That's going to give me y to the 2 minus x times 1/2 will be 2 minus x in the numerator and everything over the 2. Everybody okay with the numerator? Before we go to the denominator, let me point out that is not the same as y to the 2 minus x over 2, written like that with a slanting fraction bar. If you write it like that, that means 2 minus x over 2, whereas this one was 1 minus x over 2. So either use the horizontal fraction bar, or if you need to do a slanted one, if that whole thing is supposed to be your numerator, put parentheses around it. Questions just with that part? I'll make sure we get the notation right. Okay, we don't really need that, so let's get rid of it. Let's take care of our denominator next. Okay, I don't really want to keep putting these because I know I'm going to have to subtract. So easiest way when we have something messy like this will be to take the terms in the denominator, move them to the numerator, but change whether they are positive or negative. So we then have times a to the minus 3x and y to the plus 2x. Then just like we did before, we need to get the a's together, the y's together. We're going to have common denominators to do that. So for the a's, I've got x over 2. So I need this one to be multiplied by 2 over 2. So I end up with a to the x over 2 minus 6x over 2. So I'm going to have some x's I can put together before I'm finished. Y to the 2 minus x over 2, and common denominator again, if I multiply this by 2 over 2, I have plus 4x also over that 2. And everybody, what is x minus 6x? What? Negative 5x over 2. And y to the 2 minus x plus 4x is plus 3x over 2. So that is one way I could write my final answer. I could also have the a to the minus 5x over 2. If I wanted to, I could write the 2 over 2 as a 1 plus the 3 halves x. So a couple of different ways I could write that are equivalent. Any questions? Yes? Either one. Your preference on that. That's like saying, do I care if you do 7x plus 2 or 2 plus 7x? They're equivalent. Okay. When we have ones like this, we need to review this. We cannot move this x to the minus 3 to the denominator as x cubed. We cannot do that because of this plus sign. You can only do that when you've got a single term in the numerator and you are moving that up and down. Because of that plus, we cannot do it this way. So what we will do instead is we will take each of these little pieces one at a time. We will rewrite just x to the minus 3 as 1 over x cubed. Then we will write just the y to the minus 3 as 1 over y cubed. And we will do the same thing with parentheses to the minus 1 as 1 over parentheses to the plus 1. So 1 over xy. Everybody see that is equivalent. Then what we need to do is to look at these things that we have written down and look at those denominators, and I want the least common multiple of the little denominators, of x cubed, of y cubed, and of xy. Who can tell me the least common multiple of those 3 denominators? Or if I were getting a least common denominator of them, what would that be? Lydia. I'm sorry, Caitlin. X cubed, y cubed is exactly right. I could multiply x cubed by y cubed and get this, y cubed by x cubed and get it. I can multiply this by x squared, y squared, and I'd have that. So it's a multiple of all of them. What we do then is we multiply the numerator by that least common multiple, and we multiply the main denominator by that least common multiple. Because I have 2 terms in this numerator, I need to distribute. X cubed y cubed times 1 over x cubed is just y cubed. X cubed y cubed times 1 over y cubed is just x cubed. When I multiply in the denominator, x cubed y cubed over xy becomes x squared y squared, and that is my answer here. Not really flipping the signs, but that's not always true. And, as we've got the cubes on the x cubed and y cubed, we don't have, but we've got different exponents on the denominator. So please don't try to come up with more of a shortcut on that because it won't be true on all of them. But this general method of rewriting and multiplying by LCM over LCM will always work. Any other questions, comments? Okay, switching over to some square roots now. Okay, I see parentheses times parentheses. Anybody else see parentheses, parentheses? And Blake, what do you like to do when you see parentheses times parentheses? Let's FOIL it. So let's just start out with foiling this thing. So that will give me root 2 times 1 will give me root 2. Root 2 times minus root x will give me minus root 2x. Plus root x times 1 will give me plus root x. Plus root x times minus root x will give me a minus. Root x is going to be regular x. None of these are like terms. We cannot combine them, so we keep all four. Okay, that wasn't that bad. This looks kind of ugly at the end. Okay, let's start trying some of these that have I in them and powers of I. Now, we've got I cubed written down in our list. I to the 5th is going to be the only one we really have to factor out and figure out what's going on. When we get to this one, we're going to need to have minus 2 times I to the 4th times I. Otherwise, everything's going to be in our list, so we're going to be in good shape. What was I cubed? How do we simplify I cubed? We have that written down. This time I'll get it right. Lydia. It is going to be negative what? Negative I squared is going to be negative 1. So I cubed will be minus I. There we've got it. So we have 5 times minus I right there. Okay, we've got this thing. What's I to the 4th going to be? 1. It's going to be positive 1. So that's going to just be a minus 2I in there for us. And then we have minus 4I. And what was I squared, everybody? So I have minus 5I, minus 2I, minus 4I, minus 7. Are any of those like terms?
Yes.
Which ones? Okay, all of the i's. So Keith, if I put all of the i's together, what do I have? So negative 11I minus 7, except that that is not correct for my final answer. The reason that it is not correct for my final answer is complex numbers must always be written A plus BI. Some real number plus some real number times I. The real part must always be first, and number times I, the imaginary part, must always be last. So my final answer needs to flip that in the other order, commutative property, minus 7 minus 11I. And you don't know that it has to be that way unless I tell you, so that's why I'm telling you. Questions there? Yes? If it can't wait, of course. All right. Sometimes our imaginary problems will be things that have square roots of negative numbers in there. So first step is always going to be to rewrite square root of a negative so we have an I instead. So square root of negative 2 is the same thing as the square root of 2 times the square root of negative 1. So it's going to become square root of 2 times I. We don't need to write down the square root of negative 1 every time. You can just go root negative 2 is root 2I. And then we have times the square root of 9. And then we have 2 times the square root of 2 times I, the square root of 9 times I, the square root of 25 times I, and the square root of 49. So I've done the step of changing square roots of negative things so that they all have an I instead. So let's see what we have. Square root of 9 is, everybody? So this is a 3, so this becomes 3 root 2 I. Okay, this one is also a 3. So I have 2 times that 3 is 6 root 2. But I don't have an I have I times I, so I have I squared. Root 25, everyone? There you go. Root 25, everyone? Is 5 times I, and root 49? Okay, so I've got I, and I've got I squared, an I, and a constant. So I squared is negative 1. So this becomes minus 6 root 2. So it's real. And I have the 3 root 2i, and the 5i, and the 7. And we know we need to put the reals first, the imaginaries last, right? So we want to have 7 minus 6 root 2 plus 3 root 2i plus 5i. Except we can't quite leave it like that. We have to get it a plus bi. This is one real number and a b times I and another real number and something else times I. So we can't do that. What we're going to do instead, to show that this much is just one real number, we're going to put parentheses around it. So there's our one real number plus, and just one I, so we're going to write this as either 3 root 2 plus 5 or 5 plus 3 root 2 times I. So we're going to use the parentheses, so we have one real number plus one real number times I. Okay, enough exponents and complex, ready to switch to geometry. All right, switching to geometry. You already have those formulas down, so now we're ready to talk about the ratio of areas in similar figures. So S1 is, they tell us how long that side is. I don't know, it's 8. And they tell us how long this side is. Maybe it's 4. So they tell us that. So we could do a ratio of the sides, S1 over S2. We could figure out the scale factor. If I wanted to go from here to here, it would be S2 over S1. If I multiplied this side by that, I'd have S2. Or I could do the scale factor going the other way, would be S1 over S2. So I could get those ratios. The ratios are the same as the scale factor. But now I want to know the ratio of the area. So before we talk about the formula on that, S2 looks like maybe it's about half of S1. Would you agree? Just to kind of try to get an idea. Does it look like the area for the smaller one is a half the area of the bigger one? So it doesn't look like that scale factor is going to be true for the areas, and it's not. Anybody want to guess how they might compare if S2 is about half of S1? What do you think about the areas? Jimpy? Looks like maybe it's about a fourth. And this isn't going to be exact, but to give us just a little bit of an idea, if I tried to kind of put, there was one of those in there, if I tried to put another one in there, and another one, and then another one in there, it does look like about 4 of them would fill it up. And my figures were not exactly, my links were not exactly a half on there, but just to give us a little bit of an idea. That is indeed what is true. So if we take the ratio of the areas, or if we take the scale factor or the ratio of the sides or radii or circumferences, anything with linear units, if we square that, we'll have the ratio of the areas. It might make a little bit more sense if you think about it. If we took the ratio of the sides, we'd have S1 over S2, or S2 over S1 if we wanted to do the smaller over the bigger instead. So the scale factors would also be those same ratios. To get the ratio of the areas, we would take that fraction and square it. Put a star or something by this. These questions, and there's several different ways you can ask them, are what end up being missed the most on midterm and final for this course. So you really want to pay attention to this and get it down. I keep trying to add something to it each year in terms of explaining it. I haven't written it this way before, so hopefully that's going to be a little bit helpful to see it written out like this. As soon as everybody has that written down, we'll try an example with this, and then we'll do that very last thing of diagonals of the boxes. Anybody still need me to wait? Okay, a couple hands up there. Let's see, maybe if I do that, that might help a little bit. There still will be one more formula for that diagonal, so keep those formula pages handy. So we take the ratio and we square it to get the ratio of the areas. So we've got one circle, and its radius is r. Second circle has a radius 3/5 r. Will it be bigger or smaller? Okay, so I'm going to have a smaller one so that its radius is 3/5 of r. So that tells us, one way we could look at this, that tells us that the scale factor, if I go from the big one to the small one, is 3/5. I took this radius times 3/5 and I got the other one. If I did the scale factor in reverse, it would be 5/3. So now I want the ratio of the areas, but you've got to read the questions carefully. They want the ratio of the first circle to the second circle. Will that be big over small or small over big? Big over small. So if I am going to square this and end up with big over small, I have to say that I am going to take 5/3 and square that and get 25/9, and that is my ratio of the areas. This one was easy to see what the scale factor is. Sometimes it's not so easy. So sometimes another way to think about it is to say I'm going to take the ratio of something measured with regular linear units, not square units or anything. Here it's radii. If I want first to second, I'm going to take first radius to second radius, which is r over 3/5 times r. My r's cancel. 1 over 3/5 is the reciprocal. 1 divided by 3/5 is 5/3. So then the ratio of the areas in the same order, first radius over second radius, first area over second area, will be this ratio squared, which is 25/9. Now, sometimes the problems will be a little bit trickier. Sometimes they will say the first area is 100. What is the second area? Ideas of how to set it up. Will the second area be smaller or bigger? Smaller. So give me some ideas of how we can set it up. So jumping? Got an idea? You have an idea?
You could do 100 over 82 equals 25/9.
Okay, we already know A1 over A2 is 25/9, and we know A1 is 100. So we could just do our cross product, or we could say 25 times 4, 9 times 4, A2 is 36. Would be one way that we could do it, and then it would be some kind of unit squared. So different ways of asking you to put things together with that, but so far so good. and star by it so we don't forget it. Okay, last thing for today, last formula to derive. Your book is going to expect you to basically derive it on every single problem. We are not going to do that. We're going to come up with a shortcut formula. So on this one, they want us to find the diagonal that goes from B here at the bottom front to H up at the top right in the back. They tell us for this problem X and Y and Z over here, which I'll use in a minute. So X is this side. It's a box, so this is really a right angle on the bottom. And there's Y. We are first going to find a diagonal just along the bottom of the box that goes from B to G. So if we look just at that triangle on the bottom of the box, this is X, this is Y, and this is however long it is from B to G. Right triangle, Pythagorean theorem. I know x squared plus y squared is bg squared. So I know bg is the square root of x squared plus y squared. So now I know how long this diagonal is along the bottom of the box. So if I know how long that is now, and I'm trying to get this diagonal from B to H, I also have a right triangle right here. I just figured out how long BG is. If this height is Z, this height is also Z, and here's the part I'm trying to find. So if I draw that triangle, I have, this is the BG that I just found. This is Z, and here's the D I'm trying to find. I can use Pythagorean theorem again, and I can say that the diagonal squared that I want is BG squared plus Z squared, but BG is the square root of x squared plus y squared, and so I'm going to square that. But square of a square root gets rid of the square root sign, so I have x squared plus y squared plus z squared. That is my diagonal squared. So my formula is going to be d is the square root of x squared plus y squared plus z squared. And let's look back at what was labeled on the box so we can make sense out of those. X was the length of my box, y was the width, z was the height. So what we have is diagonal is square root of length squared plus width squared plus height squared. So when we have these, we're going to use a shortcut formula. The book has a problem like this, and they do a whole bunch of space on page 46 to work through steps like what we just did. All we are going to do when we see one like this is to say, well, the diagonal is square root of length squared plus width squared plus height squared, plug in. Length is 3. Width is 2. Height, they don't give us a number, but they tell us they want us to use the letter M. Combine anything we can. 9 plus 4, everyone? 9 plus 4 is 13 plus m squared. I use that excuse too a lot. Seriously, any questions from anyone? Okay, let me give you guys your homework sets, and we